let us dive in to talking about this precise definition of the limit. So informally, and I don't want to write it in pink, informally, we'll go, we described the limit already in this chapter as if x gets close to a, if we're saying the limit as x goes to a of f of x is L. When I write this, I'm saying essentially, informally, that as x gets close to a, then f of x gets close to L. And again, as I've said, that's too vague. What's close? Is close within 0.1? Is close within 0.01? And the answer is no, neither of those are very close. Is close to like 1/10,000,000th of the number? Is that close? No, that's not close. Close is infinitely close. In other words, it's got to be as close as I want it to be. So how do I formalize this idea? It's worth commenting that historically, the time frame that we have from when this idea came to Isaac Newton and Gottfried Leibniz to when we get the formal definition, somebody comes up with a way to actually describe it mathematically, is well over 100 years. In fact, I don't even know the amount of time. You can look up Newton, see when he lived, and look up a guy named Cauchy, C-A-U-C-H-Y, a mathematician most of you probably haven't heard of yet, but you will hear a lot about him by the end of a math major at Wayland. But Cauchy came up with this idea, whereas Newton and Leibniz, L-I or E-I, I forget what order, Leibniz, two dudes back in the 1700s, right, came up with, actually 1600s, came up with the calculus idea of limits, okay? So here's the formal definition, and I'm going to write it down in purely symbolic notation, but I want to read it to you first, and then we'll describe what each piece of it means. This is the formal mathematical definition of a limit. We say that the limit as x goes to a of f of x is L if and only if, meaning this is a definition, given any real number epsilon greater than 0, there exists another real number delta greater than 0, such that if 0 less than the absolute value of x minus a less than delta, then the absolute value of f of x minus L is less than epsilon, which sounds like a lot of gibberish if you've never seen this kind of notation before, but it is extremely powerful, and it is the cornerstone foundation of calculus, because, as I've erased it, but you can actually still kind of see it if you look just right, calculus is limits. So all of calculus is built on this definition right here. Now, I like impressing my non-mathematical friends with the ability to write things in symbolic notation, meaning I can write all of this very succinctly by using mathematical symbols that you will learn, those of you that will take the mathematical reasoning and proof class either this spring or next spring. You'll learn some of these symbols that we use when we start writing proofs. It's just because we like to make things exact and precise, but also we don't like to write a lot of words. So write this down precisely, and it says basically the same thing up here. Again, I'm going to say the limit as x goes to a of f of x equals L, and that is equivalent to, or if and only if, is what I'm defining. This limit here is defined, or if and only if, the following. For every, looks like an upside down A, epsilon looks like a backwards 3, greater than 0, there exists another number, so I'm going to write there exists. Symbolically, we write there exists with a backwards E. That means there exists a delta. Okay, this is the lowercase delta in Greek. You may have seen deltas as triangles. That's capital delta, which is often used for change in math and physics, but lowercase delta is just another variable, okay, is greater than 0. Now I'm going to use my notation for such that, actually, I think if you take Thornhill's class, Dr. Thornhill's class, he uses such that, he writes S dot T dot for abbreviating such that. I learned such that symbolically is this backwards epsilon looking thing. It's like a backwards C with a line in the middle. That means such that. And this may, again, it looks like gibberish, hieroglyphics to you, but these all mean something very precise to me as a mathematician, and will to you once you get through upper level mathematics courses at Wayland. All of this will make sense. If I wrote this on the board in any of my 3,000 and 4,000 level math classes, they know what this means. So don't just assume that it's always going to be gibberish. You'll eventually learn this. Okay, so again, the limit as x goes to a of f of x equals L if and only if for every epsilon greater than 0 there exists a delta greater than 0 such that 0 less than the absolute value of x minus a less than delta implies that f of x in absolute value minus L is less than epsilon. So our whole goal today, the only goal we have for this section, is to understand what in the world that means. And by the end of this, I'm going to do my very best to make it conceptually make sense. Okay. This is sometimes referred to as the epsilon delta definition of a limit. Okay. The epsilon delta definition. Make sure you've got it written down correctly. If you want to, you can always refer back to the OneNote. You can get to the link through Blackboard, but I want you to be able to write this precisely. And it, again, I'm going to read it. It's basically saying the same thing that's up here, that the limit as x goes to a of f of x is L if and only if for every epsilon greater than 0 there exists a delta greater than 0 such that 0 less than the absolute value of x minus a less than delta implies f of x minus L in absolute value is less than epsilon. Okay, so what does that mean? Well, let's break it down into pieces. First of all, I've introduced you maybe to a new Greek letter that you haven't used very much. It's special enough in this definition that it kind of gets this role over and over in mathematics of being this small arbitrary positive number. Okay, so I want you to think of this definition as a game. Okay, like you're going to challenge somebody to a game. We'll call it the epsilon delta game, and you tell that person, pick any small number. That's the epsilon. Okay, so you're starting the game, you say pick a small epsilon. They can pick however small a number that they want. They can pick 0.1, they can pick 0.01, they could pick 0.00 with a million zeros and then a 1. They can pick however small they want. The point is it has to be positive, and we're going to think of it as arbitrary and small. They get to choose it, okay? Then there's the delta. Okay, your job in the epsilon delta game is to find a delta so that the rest of this theorem is true, okay? If you can, no matter what epsilon they pick, you can find the delta that makes the rest of this theorem true, then you win the game and the limit exists, okay? So the delta is a positive value that this theorem, or this definition, says has to exist in order for the limit to exist. If no matter what epsilon is chosen, you can find the delta that satisfies this last statement, which we'll talk about in a second, then the limit exists, you win the game. Okay? So what does this piece right here mean? Notice that appears right here. Okay? So when you learned absolute value in algebra, right, you learned that it's this thing that you get rid of the sign, right? Like if it's absolute value of 3, then it's 3. If it's absolute value of -3, it's 3. What absolute value means is distance from 0, right? The absolute value of any number is how far away it is from 0, measuring as a positive distance, it's how far away it is. But if I write it as x minus a, like 2 numbers inside there instead of 1, it's not distance from 0, but it's how far apart are those 2 numbers. Right? If I wrote down the absolute value of 1 minus 7, this is going to tell me how far apart are those 2 numbers. The distance between 1 and 7 is 6. That's what the absolute value of 1 minus 7 means. It's the distance between them. So when you see this appear in here, this is saying the distance from x to a. How far away are x and a? Okay, so then this statement similarly would mean the distance between f of x and L. Now, if you look at the limit, remember, f of x is the output of a function, x is the input. Okay, so I'm saying something about the distance between the input and the thing that I'm approaching, and the output and the value of the limit. Okay, so this right here means the distance from x to a. This right here means the distance from the output of the function to L. So how far apart are those two things? So this statement now here will mean, first of all, since it's greater than 0, it means x can't be a, which is the part of the limit we talked about last time where we said it doesn't matter what happens at a, right? There can be holes at a, and it doesn't matter. Okay, so that's what this part means right here in the definition. It says it doesn't matter what happens at a. So x is not a, and the distance from x to a is smaller than the epsilon. Sorry, than the delta. The distance from x to a is smaller than epsilon. Okay, and there's a way that I'm going to write that to me makes pretty good sense. If I'm at, say, a value x, then my value of x, okay, on the real number line, okay, let's say this is a right here, then the furthest distance I can go from a is delta, right? So if I go over here, I go over here, I want to consider all the values for x. X can be anywhere inside here, okay? Not here, but not here, but anywhere in between, so that the distance away is at most delta, right? This distance here is at most delta. So that makes this value right here a plus delta, and makes this value over here a minus delta. Okay, this means that x is not a, and x is somewhere between a minus delta and a plus delta. Because this says that the distance from x to a is smaller than delta. I'm like within an interval, I'm within a circle of a where the furthest I can go is delta. Okay? And then this statement means almost exactly the same thing, only now in terms of f of x can only be epsilon away from L. And I like to do this one vertically because it's actually the y-axis. If this is L, then the highest and lowest I can be here, the distance away, is epsilon, which makes this L plus epsilon, and this is L minus epsilon. So f of x has to be somewhere between L plus epsilon on the top end and L minus epsilon on the bottom end. That's what that piece means. Okay, so you know what all the meanings of the pieces now are, but let's think about it again in terms of this epsilon delta game. So for the limit to exist, for there to be the limit as x goes to a of f of x to equal L, means that if you let somebody else choose a small epsilon, that you can choose a delta small enough so that for all of the x's within your delta of a, all the outputs for those x's end up being inside of the range L plus epsilon to L minus epsilon, right? You can get however close you want to L by getting close enough to A. So let me draw this picture for you, okay? The red line on my graph, I know it's gray on yours, but the curve itself is y equals f of x. So let's say somebody has chosen this epsilon, I didn't even give it a numerical value. I'm just saying it's that big. So I've gone above L that far and below L that far and drawn horizontal lines. Okay. The question is, how close do I have to draw an interval around A so that everything inside that interval maps or has a curve inside the blue area? How close do I have to get? Okay, and if I can get close enough that everything maps inside the blue area, then I'll say that limit exists. So what I would do is I look at this thing and I see this point right here and this point right here. Okay, I'm going to draw this line straight down. And I'm going to draw this line right here. I'm going to go up and down from here. You notice that between these, in this little region right here, every value in here, right, if I apply F to it, maps inside the blue area. So what I'm basically asking us to do is to find a delta so that if I go that distance away from A on either side, everything stays inside there. Now, if I chose my delta, don't write this down, I'll put this in gray. If I chose this to be my delta right here, then that length, I would have to go in both directions, and I would be saying this interval right here maps all the way inside the blue area. But that's false, right? It doesn't, because there's some points over here that don't map inside the blue area. So I wouldn't want to choose the larger one of those two sides. What I want to do is choose the smaller one of those two. I'm going to let this right here, this distance here, be my delta. Because if I go that distance to the right and that distance to the left, okay, that implies that every x in A minus delta to A plus delta outputs in the blue, right? So that's the delta that I would choose in that case. And if I made the epsilon smaller, I would choose a smaller delta. But what we're trying to claim here is that no matter how small of epsilon we choose, we can find a delta that will be close enough to A that everything within delta of A maps or has an output inside of this interval here, the vertical interval from L minus epsilon to L plus epsilon. That's the concept of a formal definition of a limit. We can get arbitrarily close to L by finding values sufficiently close to A. All right, now I can kind of reinforce this with a few practical examples. I'm going to do it numerically first, and then we're going to do it proving in general for all epsilon. So the first few examples here are what happens if I give you a specific epsilon, a number value for epsilon. Can you find the number value that goes for delta that makes that statement true? Okay, so the first example I've given you actually is a graph. Okay, this graph right here, the blue line, is y equals f of x. Okay, and I want to play the epsilon delta game, and I'm going to do it by having somebody choose the epsilon to be 0.2. There's the epsilon. Okay, so really what we're looking at is this statement that the limit as x approaches this value right here. So it's the value in the middle down here as x approaches 1 of f of x. And what is the limit as x goes to 1 of f of x in this picture? 1. It looks like 1, right? That's what we're going to try to prove with the epsilon delta definition eventually. Okay, so this one right here, and maybe I'll do this in light green. This one right here is this one right here. And this one right here is that one right there. Right? Remember from the definition, this was x minus a, so a is the thing that x is approaching, and this is f of x minus L. L is the output of the limit. Okay? So remember that this statement right here means that we're trying to map within 0.2. Our outputs need to be within 0.2 of 1. Okay? So what's an output of at most 0.2 away from 1? It's 1.2. That's where this 1.2 came from. That's 1 plus the epsilon. Okay, this is L plus epsilon. This is L minus epsilon. And so if I look at the graph and I go, what input gives me 1.2? They tell me that that's 0.7, right? This says f of, say, 0.7 is 1.2. And over here, I also know that f of 1.1 is 0.8. That's 1 minus 0.2. So the question here is find the delta. Find the delta so that when x is within delta of 1, when x, the distance from x to 1 is smaller than delta, then all the outputs are within 0.2 of 1. That is, they are at most 0.2 away from 1. So which delta would I choose? Am I going to choose this delta right here or this delta right here? The second one, right? So what is that delta? That distance is 0.1. That's your answer from that picture. So it's really easy to do when I give you a graph with all the information like this, but you need to understand what it's asking for, right? How far away can I get from the A so that everything in that distance from A stays inside this interval right here, right? When you output it. Did you get that? Okay, I feel like I'm over-explaining, but I feel it's like a difficult concept to get in general, so I'm intentionally over-explaining. Okay. Cool? Yes? So if you got a picture, I didn't give you a formula for F, I just gave you a graph with the epsilon already drawn on here. Let's do it where I give you a picture still, but I don't give you all the numbers. I'm going to actually give you the function itself. So f of x is x squared. So it's this parabola right here that you recognize. Okay. So over at 1, the output is 1. And we're trying to find a number delta so that the distance from x to 1 is less than delta, implies or forces the distance from the function to 1 to be less than a half. Okay? So where is this 1 on my picture? Is it this one on the y-axis or the x-axis? X-axis, right? And this one right here is the y-axis right there. And so this value right here would be called what? Epsilon. And where is epsilon on this picture? It's the distance away right here, right? There's epsilon equals a half. So that's why I'm at 1.5 above and 0.5 below. I'm taking 1 plus epsilon and 1 minus epsilon. So I go over to the curve and I say, okay, so what input gives me 1.5? Can you figure out what these two numbers would have to be? How would I find this, say, this question mark right here?
Plug it in to the formula.
So what am I plugging into the formula? I assume you mean this formula, right?
Yeah.
Okay. So we know that f of x is x squared, right? And what's the height of this curve right here? 0.5. Now where does 0.5 go? Is that the x or is that the value of the function? So 0.5 has to be the output, right? So then what's the input? Exactly. I wonder if I can open the calculator. Remember the last time I was trying to open the calculator and it just closes? I don't understand this. That is so weird. All right, what's the square root of 0.5? Actually, I did it in my notes here. Should be 0.707106. Okay, for this, so that's 0.707106 right there. What's the other question mark? How would we figure it out? Okay, so it's going to be square root of 1.5. So x turns out to be 1.2247. Now you can kind of tell from the graph, but even if you drew this by hand and you weren't sure which one was bigger, we need to find how far these are away, right? Those aren't the actual deltas, because the delta would be how far away that I get. So if I call this, say, delta 1 and this delta 2, just so I can write it over here, delta 1 is the distance that this number is from 1, which is like absolute value of 0.707106 minus 1, which gives me 0.292894 in my calculator. That's this distance right here. And then my delta 2 have you all figured out how to write down deltas quickly? Like, you probably haven't written the letter delta like this very often. It looks like an S, and then you close the loop. I didn't teach you how to write the letter delta. You probably just watched me write it, but there you go. It's actually how I sign my name. It looks, I don't like the cursive S. When I learned cursive whenever I was in, what, 3rd grade or something like that, and we learned to sign our names like that. I don't like that S, so I don't use that S. You know what I use? That S. It looks like an S. It's kind of cursive, and it's a delta. So my name is actually Descartes, because I'm using the Greek letter for D. Just saying. Okay, so there's my first letter initial there. And then this one would be the distance from, say, 1.2247 to 1, x minus a again. And that distance is 0.2247. So which one of those should I choose as my delta? 2247 is my choice for my delta. This is not a proof. This is just one instance of the epsilon delta game. You're letting somebody choose the epsilon. So maybe I gave you, instead of a half, what if I gave you 0.1 or a tenth? Could you repeat this process and get the delta that would work for that? You're going to have to do some of these on your own in your homework. This is just a single case, not a general proof, but a single case of given an epsilon, can you find the delta that makes it true that this statement right here holds? Okay, that whole statement right there holds. And this can actually generalize to an actual practical situation where we can talk about things in terms of precision. Let's say, for example, a machinist has to manufacture a circular metal disc whose area is exactly 1,000 square centimeters. So first of all, he needs a device that's going to cut out a circle. So we're going to assume this device that he has somehow allows him to set the radius of the circular disc he's going to cut out. Okay, and with all things in the real world, he can't get exactly 1,000 square centimeters. There's going to be a little bit of error tolerance, right? How precise does it need to be? So first of all, if he could do it precisely and exactly, what would need to be the radius of his disk? Simple geometry problem. What's the radius of the disk that gives you an area of 1,000 square centimeters? How would you figure that out? You know the area of a circle? area is pi r squared, yes. And what do you know in this case? Area is 1,000. You also know pi is that irrational number, 3.1415926, so on forever. And so r squared. So if I divided the pi across and took the square root, that means r would have to be the square root of 1,000 divided by pi. Agreed? Agreed. Which I did in a calculator is approximately 17.8412 square centimeters. So if the machinist is allowed an error of plus or minus 5 square centimeters in the area of the disk, how close to the ideal radius in part A must the machinist control the radius? So what does that mean? That means I can go up to, at most, 1,005 square centimeters, or all the way down to 995 square centimeters, and that's okay. We're allowed that amount of error. So now we need to come up with what's the smallest range and the largest range, or the smallest value of the radius and the largest value of the radius that I'm allowed to have. And whichever one of those is closest to this number, I'm going to choose that distance away as my tolerance. Does that make sense? Like, I know that on my radius axis, I've got to get close to square root of 1,000 over pi, right? But I can go, I'm gonna choose some level of tolerance for my radius. And I want to choose it small enough so that everything within that range, okay, is within 5 square centimeters of the desired value of 1,000. Notice that's the same question we were just asking in the epsilon delta game. Only now it's got a real world practical case. So how would I do that? Well, I would find what is the radius that goes with 1,005 square centimeters. And what's the radius that goes with 995 square centimeters? So this would mean that this r up here would have to be the square root of 1,005 divided by pi. And I don't trust my notes on this one, so I'm going to do this on my phone calculator here. I'm going to take 1,005 and I'm going to divide it by pi. And then I'm going to take the square root of that, and I get 17.8857, actually 58 if I round it. And then this one down here, if I go down to 995, that means my r would be the square root of 995 divided by pi. Y'all see where I get those numbers, right? It's from this plus or minus 5. So those are the values of my r. And so if I take 995 and divide that by pi, and then take the square root of that, I get 17.7966. So one of my deltas, that is one of my distances, is the distance from this x here, 17.8858, to the A, which is 17.8412. That's cool. My phone is smart enough to read my face through my face shield. That's cool. Can't do it with my masks on, but 17.8858 minus 17.8412. 8412 is not that. I tried that again. 17.8858 minus 17.8412, 0.0446. And delta 2 would be 17.7966 minus 17.8412, which is it's the same number, 0.0446. So what should I choose as my tolerance? I would choose this. And by the way, these are all centimeters, right? This was not square. This is just centimeters. This is centimeters, centimeters. So I would choose this as my tolerance. That's how close I need to be. I need to be within 0.0446 centimeters on my radius to make sure my area is within 5 centimeters squared. Okay, it's an empirical way or just a numerical way to do that problem. Okay. Yes, questions? Why did I choose specific values? It might help. I didn't do it beforehand, but I'm going to do it now. It might help to think of this in terms of the definition of the limit again. In this case, thinking of finding a limit as an input and an output. As input goes to A, what the output goes to L. What is the X in this example? Okay, just as a quantity, what measurement is the X in this problem? What's the input to my formulas? Okay, the 1,000 is the area, and that's the thing that I wanted to be within this given value. So you think of this plus or minus 5 as the thing that was given, right? So what are we given in the above problems? What was the thing that we were asking somebody else to pick for us? It was the epsilon, right? And so the epsilon always has to do with how close the output is to the limit. So the 1,000 is the output. Does that make sense? Which means the input is what variable do we plug in to get the output? If the output is area, what's the other variable? It's the radius right here. So I would say that the X in this, the input, is the radius. And the output, the value that we're wanting to see get close to something else, is the area. And what am I getting close to? What's the A? That is, what does the radius need to be close to? Well, it needs to be close to the exact value. It was this 17.8412 value right here. Right? So this is the square root of 1,000 over pi, and the L is the 1,000. And then the epsilon that was given, that was the 5. And then the corresponding value of delta, that was the 0.0446 centimeters. All right, I'm going to run out of time before we get to this section 3, proving limits, so I'll just bump the rest of from 3 on. But let's do, in the last 2 minutes of class, let's do one together that doesn't have a picture and doesn't have context. Let's just see if we can't do it for a specific value of 0.1 and see how we would do it without even using graphs. And we'll do the proving limits in class on Friday. Okay? So, this problem, very similar to the one above, except now my f of x is just given in the formula. So we want to figure out, what does delta have to be? How close do I have to be here in order for 4x minus 8 to be within 0.1 of this. So what is f of x getting close to? It's getting close to this number right here, which is the L. So I could write this as the limit as x goes to something of something equals something. What does this statement right here tell us goes in those blanks? What goes in here? The thing that x is getting close to is inside here. So it's 2. And this is the f of x, so what goes here?
4x.
And then over here. Okay, and now I'm going to say, if you go back and look at the definition, notice way back up here, the minus sign is built in, right? Because it's built in, you don't choose it, you leave the minus sign where it is and just take the 8. This is what we would be trying to claim and prove. Now, how do we do that? How do we find how close we have to get? Okay, let me give you a shortcut. You start by writing this down, 4x minus 8, and say that has to be less than 0.1. Okay? Which means, by the way, the same thing as saying that 4x minus 8 has to, because its absolute value means take away the plus or minus if there is one, it has to be smaller than 0.1 but also bigger than negative 0.1. One of the tricks you learn in algebra is that you can rewrite these absolute value inequalities. And I'm trying to get x minus 2 in here. So what I would do, and I'll have to explain this more next time because I'm out of time, but if I divide all 3 sides of this inequality by 4, do you notice that I've got an x minus 2 in here? You can divide all 3 sides by that. What is 0.1 divided by 4? 0.025, so this is less than 0.025, and this is greater than negative 0.025, which I can apply the same trick I just did from the first line to the second line to reverse this and write this as x minus 2 has to be less than 0.025 in absolute value, which makes that my delta. Using graphs and table cannot prove the existence of a limit. Mathematics requires the rigorous application of logic to formally prove claims. Maybe that should be to or proving claims, sorry, grammatical error. To formally prove that the limit as x goes to a of f of x, we must use the precise definition of the limit, that, by finding delta for any given epsilon. So far we have started with a specific value, but to prove this, we must find delta as a function of epsilon. And so my proofs are going to be in basically 2 steps. I'm going to do what I call a preliminary analysis of the problem. That is, I'm going to use a little bit of algebra to guess a formula for delta, and then I'm going to formally write out the proof. Okay? And just so that I'm consistent with the terminology that the homework uses when you're doing these proofs, you do have to do these proofs in the homework, but I'll show you before the end of class how WebAssign has you do the proof. It's basically a drop-down box of filling in the blank of what words go in each space in the proof. Okay, so that's as extensive of proving that I'm going to ask you to do in here. I got to find it in my notes. I annotate. I mean, I could prove this off the top of my head, but I would use different words to describe this. So let's just make sure that we do the pieces in the right order. So our preliminary analysis starts with the f of x minus L is less than epsilon. Starts with our goal, okay? What we hope to prove. So really the preliminary analysis is, let's work the proof backwards before we actually formally prove it. What is our goal? Our goal is the thing that we want it to imply, right? We want to find the delta so that that very last inequality is true. So start with the last inequality, okay? So what is my f of x in this limit right here? This guy right here. So I would say the absolute value of, I'm not going to do f, I'll go ahead and write the formula in there. It's the f of x, but it's in parentheses, all right, 4x minus 5, okay, minus its limit, what it's going to. What is 4x minus 5 getting close to? Careful. So you got to remember, there's two things getting close to something, right? X is getting close to something, and f of x is getting close to something. So what is f of x getting close to?
7.
The 7, and then while the x is getting close to 3, right? So this is 7 here, and that has to be less than epsilon. Now we don't have a specific value, so we're just going to use epsilon, okay? Now eventually what we want to do is we want to turn this into, and I'm going to put this in a thought bubble over here. What am I looking for? I'm looking for x minus a, which is 3, less than something. Okay? I want to somehow turn this into this, where the something will have some epsilons in it. Okay? And for linear ones, it's really not that hard. You'll see right away. It kind of just, it falls in your lap when you do a little bit of simplifying, right? Because 4x minus 5 minus 7 is, in absolute value, 4x minus 12 is less than epsilon. And if I'm trying to get to x minus 3, notice I could factor out the 4, right? If I pull the 4 all the way outside, I'm left with that, right? See how it just fell in our lap? And then to get the x minus 3 in absolute value by itself, okay, I divide the 4 across. Divide both sides by 4. You get that x minus 3 is less than epsilon over 4. So this is my delta choice. And that's what I call this preliminary analysis, because it's not a proof. You can't, when you prove something, as you will learn, and you saw this in geometry in high school when you did, very briefly, you talked about geometric proofs. Some of you, depending on who your teacher was for geometry in high school, would have done more proofs than others in here, but you at least proved a little bit about like corresponding angles of congruent triangles are congruent. Does anybody remember CP/CTC from their algebra, or not algebra, their geometry? Or vertical angles are congruent, you know, whenever you draw two lines together, these two angles have to be the same. You're proving things like that in geometry. Okay, so whether or not you remember that or not, here's the point. With logic, if you're going to try to show that A implies B, you can't assume B is true and figure out what the A is that makes it true, right? That's not how you prove things. You have to start with A and eventually turn it into B, right? So what did I just do? I started with what I wanted to prove, and then I found the delta that makes that true. That's not a proof. That's me kind of brainstorming how will the proof work. Now what I've got to do is I've got to start with the thing on the left of the implies and prove the thing on the right is true. Okay? And again, I keep saying this, the extent of proving that you have to do in this class is really very limited. You will learn a lot more about logic and proving, everybody in here that has to take proofs. So let's actually write out the formal proof then. Okay? So what I would do to formally prove this is I would start with, let's let delta equal epsilon over 4. So we are given an epsilon. Let's choose delta to be 1/4 of epsilon. Okay? So we start with what's on the left-hand side of the implies. That is, we're going to assume that 0 is less than x minus a, and a in this case is 3, is less than epsilon over 4. Okay? Then, now we're going to try to show that the second inequality is true. What's the second inequality? Well, it starts with f of x, which is 4x minus 8. Nope. Is it 8? 7, sorry. Minus L. Did I do that right? 4x minus 5 and then minus 7, sorry. The function is 4x minus 5, right? And then the minus 7 is the L part, yes. So start with this. We have to show that that's less than epsilon, right? Well, first of all, just by algebra, this is 4x minus 12, right? By algebra. You don't always have to write out the reasons like you did in geometry, but it needs to be clear to whoever's reading it that that's clear. We just collect like terms, right? And then that's also equal to 4 times x minus 3, right? By factoring. So see, I'm starting with assuming what delta is. That is, I've got to guess now. I start with the left-hand part of the proof, and now I've gone to the inequality. I'm trying to show that this is less than epsilon. So I did some algebra. I did more algebra. Now, what do I know about this? What did I assume? I assumed it's less than epsilon over 4, right? So I can say this whole thing now is less than, leave the 4 there, and x minus 3, the absolute value of it, is less than epsilon over 4. So just think like, oh, trig proofs. You also did proofs of trig identities, right? We talked about this in my trig class. I'm sure you did it before. You start with one side and try to show it's the other side, right? So I've started with one side of the inequality. I'm trying to get it less than epsilon. So each time I take a step, I got to do some rule that's valid. So I've done that, and now 4 times epsilon over 4 is epsilon. Done. I just proved that if I assume this, then 4x minus 5 minus 7, f of x minus L is less than epsilon. So illustration-wise, we have found that if we want to be within epsilon of 7, we have to be within delta equals epsilon over 4 of 3. That's how you do a proof. So what the definitions so far have forced us to do is consider limits from both sides. I don't know that I really emphasized it, but you remember when we did graphs, to have a limit, you had to have the limit coming in from the left and from the right, right? Be the same thing. So picture-wise, and I'll come down on the next page. You don't have to draw this, but imagine that you've got a curve that does this, and this is your A, okay? And maybe this is the L. This limit doesn't exist, right? Limit as x goes to A of f of x does not exist, D and E, right? And why does it not exist? According to the precise definition of the limit, why would this not possibly exist? It doesn't exist because no matter what epsilon you choose, right? As long as the epsilon is less than like this distance between these 2 points, say that's epsilon or L minus epsilon and L plus epsilon. Notice if you go around this for any delta, no matter how close you get to A, there's always something to the left of A, right? In this interval around here, which means there's always this piece of output down here, okay? You're always, no matter how close you get, no matter how small delta is, you're always going to have some piece down here that is not inside this region right here, right? Because for the stuff on the right-hand side, sure, this stuff over here is inside the green, which is what you want, right? But the yellow is always outside the green, no matter how close you get. That's why the limit doesn't exist. Because there's no delta that you could find that's close enough to A that everything inside that interval, with the exception of A, is inside the green, right? Because of this piece broken down here. But you can find the limit as we approach from the right, right? The limit as x goes to A, and how do we write from the right? Plus f of x is equal to L. So what's the precise definition of maybe this? And if I called this maybe M, I could also write the limit as x goes to A minus of f of x equals M. So what I'm going to do in order to define these two is that I'm going to only look on one half of this interval, each direction. Okay? If I can find a delta to the right of A, okay, so that everything to the right maps inside the green, then I'll say the limit from the right exists. And if I can find a delta so that everything to the left of A but not above it, okay, is mapped inside the green, okay, then the limit from the left exists. So if you go back to my blanks, right, such that if what I will put in there is that instead of saying the absolute value of x minus A is less than delta, I'm simply going to say that x, okay, and this is for from the right, so x is bigger than A, but less than A plus delta. Notice again, what this means, you know, in a visual, is that if this is A, that I'm talking about it should be open here, where this is A plus delta. Everything inside here, right, maps. You can find a small enough delta that everything to the right of A, but within delta of it, its output is within epsilon of L. And if I wanted to go the other direction, if I wanted to define the left-hand limit or the limit from the left, I would say, what do you think? What goes on the left-hand side here? A minus delta, because it's to the left, right? To the left. I can go further down, but I'm not going to go any more to the right. So the right-hand side is going to be just A. So this picture would look like if this is A, right, open dot, going down this direction to A minus delta. You don't have to write those pictures, but that's what I'm visualizing in my head. You only have to do half the limit, okay? Now, I'm not going to formally prove this, but there is a theorem then that we could show. It's not immediately obvious, but it's fairly easy to prove. You can say that if the limit as x goes to A from the right of f of x equals the limit as x goes to A from the left f of x equals L, then the limit as x goes to A of f of x is L. That's just, I threw that in because I'm thinking of it, and I have time now because I've split this lecture into two. What does that say? That statement right there that I squeezed in there says if the limit from the left and the right are the same according to these definitions, then I can prove that the other definition holds. I won't walk through the proof, but I'm just going to tell you that that's true, which is it's a validation or a verification of what you already know, that when you look at a graph, if the limit from the left and limit from the right go to the same number, then that's what you say the limit is, right? Cool. And then the last thing, the only other thing we haven't done so far that we did see in previous examples is what happens when a function goes like that, right? Maybe from the left and from the right, they both explode, okay? We had a name for that. We called it infinity, right? We would say that the limit as x goes to A of f of x is equal to, and we use that infinite sign. So this definition doesn't work for infinite limits. You have to do something different because, again, think of the picture down here. In order to define it precisely, you have to have an L and then go on either side of it. But with infinite limits, they go up forever, right? There's no L, right, that you're going to get with an epsilon of, right? So I couldn't draw an L and then go with an epsilon and try to map inside there. So what you do with infinite limits is a picture that looks like, and I'll just draw it real small right here. Let's say this goes around this A. Okay? So instead of saying that we're within epsilon of L, we're simply going to say no matter how high you draw a line, the function always gets above that line. Okay? So how I write that as a definition is that we would say the limit as x goes to a of f of x is infinite. And that's a new phrase. If you saw it in my previous definitions, IFF actually stands for, where was it? Just so you see it, I've already written it. This phrase right here. Oh, don't mark it out. Highlight it. IFF is just my abbreviation for if and only if, which is the same thing as the double arrow up there on the top line right after the L. Okay, if and only if means the thing on the statement over here is identically the same as the statement over here. They mean the same thing. This implies this and this implies this. They're identical to each other. That's what a definition is, saying that this thing right here is exactly the thing after the if and only if. So just another way of saying IFF is to say is defined as. So the limit as x goes to a of f of x equals infinity is defined as saying pick any positive number. Instead of picking epsilon, pick a positive number, that there exists a delta such that if x minus a is greater than 0 and less than delta. So that's the same statement as we saw before, that we're within some region, some delta of a, then my function gets bigger than m. For it to be an infinite limit means that you pick a big number, the biggest number you can think of, okay, that I can get close enough to a that the output of the function is always bigger than that. That's what infinite limits mean. And to be negative infinity means you pick the smallest, that is the lowest negative number you can think of, right? And that I can get close enough to a that the function is always even less than that. Okay, that's what it means to say it goes to negative infinity. Okay? So this would be one that was in your notes, in your homework. So I go ahead and give you the pieces to this. It looks almost like the proof we just did in the homework, only now I'm going to use the one-sided limit definition, right? That instead of picking epsilon and finding delta, I would pick m and find delta. And the m is I'm trying to get bigger than that m, or let me be less than the n. Okay? So first of all, this right here is a combination of two ideas. It's got the limit from the right, and it's got a negative infinity that I'm trying to get to. So since the output of the limit is negative infinity, I'm going to use this definition right here. So given n less than 0, that's from this definition right here, we need delta greater than 0. Now, I'm not going to use this blank because I'm only looking at the limit from the right-hand side. So if I scroll up just a smidge, here's the interval around x that I need, since I'm taking the limit from the right. Okay? So I won't write 0 less than absolute value of x minus a minus delta. I'm going to actually write from x, okay, bigger than a. And what's my a?
0.
And less than a plus delta, which is, again, 0 plus the delta, 0 plus delta is delta. Oh, I got that. Sorry. Hope you were doing pencil. That's the whenever part. I meant that in that blank. What do we actually want? We want this blank to be the f of x minus L. So f of x is log of x. So that should be natural log of x is, and this is back from that definition, we need this. We need that to be true whenever x is between 0 and delta. Now think about this. Natural log of x is less than n. If I wanted to solve this for x, how would you get x by itself in this equation? Does anybody remember that from your algebra? We did talk about it in our very first lecture for how you get something out of a natural logarithm. I wanted to solve this for x. It has the e part in it. That's exactly right. The opposite of logarithms are exponentials. So you take the exponential of both sides. So if I write this as e to the natural log of x, that's going to be less than e to the n. But then e to the natural log of x cancels, right? And x is then less than e to the n. Okay, so the nice thing about that is that's exactly what we wanted to get, x less than something. And the something is this guy. So we're going to choose delta to be e to the n. So if x is less than e to the n, then the natural log of x has to be less than n, and that means we finished the proof because that was what we were trying to show. Trying to show that the natural log of x is less than n. That will help you if you follow that process on the one homework problem that I've got on there that involves a infinite limit. Okay. I know that's confusing. I told you from the beginning this is probably one of the most abstract and conceptual things that we do. What I really hope that you get out of this most is that you understand the concept of the epsilon delta game. That limits, by definition, mean no matter what epsilon you choose, you can find a delta so that the output is within epsilon of the value of the limit, or the output, right, is within that epsilon of L if you're within delta of the input. Given epsilon, you can find delta. Given epsilon, you can find delta. Okay? And what is epsilon delta? It's these things, right? So those are the big concepts that you've got to understand. And if you do that, then you should be in pretty good shape, especially on the homework, but also on the test. Okay? The good news is most of what we do with limits, we can get away with what we learned in the previous two sections. I just wanted you to see that there's a formal mathematical foundation to our rule of thumb, limit laws, and looking at pictures. We can do those things because this is solid mathematical rigor.